So in the last video, I solved questions about rockets and the thrust equation, right? So the way I derived the whole equation is that I actually assume that the external force, is just applied on the rocket, and there's no force on the gas. But there should be a force on the gas when the rocket is just starting to launch, right? There's gonna be some force from the ground on the gas or something like that, right? So what about those situations? So I made a whole video on it, right? Yeah, that's like a really short derivation of the actual thrust equation, so the general thrust equation, which is not just limited to rockets, but I mean like all kinds of things like balloons, and balloons also rocket, by the way. But yes, all kinds of stuff. Helicopters, if you will. Right. It's not as general as it should be, because I still did not take into account the fact that um, the general propelling machines, will they take something inside and then throw it out with a higher velocity so that they can propel themselves, right? So that's what like a fan does. So that's how helicopters work, right? So I didn't take this mass being taken inside, right? Yeah, that I didn't take into account, but I did take the fact that the pressures will not be zero everywhere, right? I did take that into account, and that's why I'm saying that that equation is more general. But anyway, so 180 done. And yeah, like this equation is very much correct. Here F should be the external force on just the rocket, not the gas, right? Okay. And yeah, there's supposed to be some pressure terms as well, but then I think uh, they have assumed that F also contains those terms, right? So yeah, just check out my derivation. You'll see what I'm talking about, right? There's going to be some forces because of the pressure uh, that the gas will build up, right? Ejected gas will build up over time if it is not just ejected into vacuum, right? If it is ejected in a some kind of like container or something. So if you have this kind of thing, so you have a balloon. Oh, sorry, this should be now full screen. Right, so if you have something like, I don't know, a balloon, and so balloon has a bit of an ending over here, and then you have this inside a tube, right? And then you block this tube, so you close it from one end, and then you leave it open from another end, and then you let this balloon go, right? So it will propel itself by using air, but what will happen is that the air that will eject out, it will hit this surface, and yeah, this whole cylinder is just on the ground, so friction is holding in air. Okay, and this is, I don't know, just assume it's a very long frictionless cylinder. Okay, what will happen is that air will hit over here, and then over time you will have a bit of pressure building up over here, right? Yes. That is if the balloon is not going faster. So I don't know, just put a very heavy block in front of it, something like that. So even if there is a friction for this block, I mean that friction is constant and stuff. So yes, so what will happen is that you will have pressure building up, and because of that, the balloon will have a higher thrust than what we expect. So the expected thing will work if there's no closing over here. So it's just the balloon. You have this stream of air going out, and then you got this block which this is moving. Yes. So the thrust that we'll get in this condition, it will be less than this condition. So, right, you have to take that into account. That's what I did in the derivation. But over here, what we'll say is that, okay, this force, because of this pressure on this balloon, right, we'll just take that to be inside this F as well. And also this force actually on this balloon, right? Yes. Well, actually not this thing. So if we are considering this whole thing to be a rocket, then you would be talking about this force. So this pressure times area thing, you will also take that into account. Yes. And of course, we are assuming that it's a sealed tight kind of situation, that this balloon is yeah, not letting this air go from here to, and even if it does, there's this block which will not allow the air to escape, right? Okay, so that's understandable. Anyway, let's go to 181 now. A spaceship of mass m naught moves in the absence of external forces with a constant velocity v naught. To change the motion direction, a jet engine is switched on. It starts ejecting a gas jet with a velocity u, which is constant relative to the spaceship and directed at right angles to the spaceship's motion. So the spaceship is going like this. To change the motion, a jet engine starts ejecting a gas jet with velocity u, which is constant related to the spaceship, okay, and directed at right angles to the spaceship's motion. So if this is going like that, then it might be, I don't know, over here, so that you have a propellant force on this spaceship like that. So it might be going into a circle or something like that. I don't know. The engine is shut down when the mass of the spaceship decreases to m, okay. Through what angle alpha did the motion direction of the spaceship deviate due to the jet engine operation? And it has to go with constant velocity v naught. We just don't. We just want to change the v naught thing. We don't want to change. Sorry, just want to change the direction. We don't want to change the magnitude, right? Yeah, just the direction, not changing the magnitude, of course. So then it should be a case of a circular motion, right? Yes, because this velocity should be perpendicular to this thing. I mean, that's going to happen in any case, right? And then u is always perpendicular to that. That's what you're saying. Relative to spaceship. Oh yeah, the spaceship has a different coordinate system. According to spaceship, like yeah, along this length you have the x coordinate or something like that. So if it starts rotating, right. So according to spaceship, it's like that. But then maybe its velocity is different. Maybe its velocity is somewhere over here. Then in that case, you will have um, work done by this force on the spaceship, and that's the bad thing. You don't want the velocity to change, right? Yeah, well, wait a second. Wait a second. The energy will change anyway, right? It's half mv squared, and that should change. But yeah, you get the idea. Like, okay, this velocity is always perpendicular to this guy, always, right? Yes, it's perpendicular to the motion. And also it is constant as seen by the spaceship. So this motion direction is also constant as seen by the spaceship, right? So it might be along this, yes, okay. It really looks like a circular motion. Through what angle alpha did the motion direction of the spaceship deviate due to the jet engine operation? I mean, what's the acceleration though? Acceleration we can figure out, okay. And then it's always perpendicular. So when I'm thinking I can use complex numbers for this, so let's just say that this velocity is pointing, so if this is the x-axis, this is the y-axis or something, then this is pointing, and this thing is like theta or something. So this is pointing in e power I theta, this is pointing in e power I theta minus y upon 2, right? And then you can write down some equations for that. Yes, so you can add an acceleration and then equate that to dv upon dt, and that will give us a nice thing. Yes. Yeah. Through what angle alpha, right? So just do it. Just do it. First of all, figure out the acceleration. So we'll use this equation that we always use, which is ma is equal to mu times u vector plus the f vector is just 0, and then there has to be some other stuff, but then that's not actually going to be important because the pressures are not there. There's just zero pressure in the vacuum, right? Yes. So yeah, I mean, I'm using my equation that I derived, so the general one, not the one given to us to prove, which I think is correct. I mean, like, that thing is very much correct for a basic understanding that in vacuum, how would this be, right? But if it's not vacuum, then you have to consider the pressures. Okay, anyway, this is our equation, right? So u vector, yeah, that is kind of a constant thing, right? As seen by this spaceship, of course. And let's just say, okay, spaceship's velocity, so v vector is, I don't know, v naught e power. Is this going to be v naught? Is this v naught going to be constant or? Right, initially it's moving at a constant velocity, but then we have to change the motion. I mean, of course, we have to keep its velocity constant, but change its direction. So there we go. V vector is equal to v naught e power I theta, right? So maybe this is going in this direction. That's how the spaceship is going with v vector like that. And there's acceleration in this direction. This is our real axis. This is our imaginary axis or something. So then of course acceleration is actually like, okay, yeah, write that as a complex number. So it's going to be mu upon m, and u vector should be in this direction or something. Mu is going to be negative, so we should just put negative mu so that we get the actual thing. Wait, what? Oh, sorry. Oh yeah, u vector will also be negative, right? So but we are going to put the magnitude, so we have to put this negative right there. So mu will just be dm upon dt, right? Okay, this times u, and then you got I e power I phi, sorry, e power I theta. So right, this is the x and y coordinate, but actually what will happen is that this spaceship is going like this, and acceleration vector is like that, right? That's for the general case when you have theta. This is for the original, so initial situation. Yes, you got this thing, which is also just equal to dv upon dt. So that's going to be equal to iota e power I theta v naught, and then you got d theta upon dt, which I'll call omega. Yes, okay, right. So u is constant, v naught is constant. Well, this cancels anyway. All you have is like, okay, v naught omega is equal to negative dm upon dt will add upon m, so dm upon m dt times u. So u is a constant number, we don't have to worry about that. And then this omega thing is just like d theta upon dt for sure. Hey, what does that mean? Yeah, this means this thing. Okay, so we can just integrate it right away, and you will get v naught. So change in theta, which is like the deflection, which they are saying is alpha, right? Yeah, deviation. So that's our alpha. That's equal to yeah, this thing. Like it's gonna be natural log of m naught upon m, and that times u. Yes, right. The engine is shut down when the mass of the spaceship decreases to m, right? So till that point, we can figure out what our deviation is going to be. It will jet engine operation, right? So that's it. This equation tells us our alpha, and that's it. That's all you need. I mean, they give the mass and everything. So it's weird how somehow, without even thinking about the things as a function of time, it somehow still works out, right? In reality, what we do is that actually once we have this, plug this into one of the other equations and then figure out the time dependence, so that we can answer any kind of question. But in this particular case, you don't need to do that, right? So there we go. So it has decreased to m, and initially it starts off at m naught, and that's what we did. Okay, right, this is our equation. There we go. So 181, this is our answer. Alpha is just all of this stuff, and then upon v naught. Yes. Okay, 182. A cart loaded with sand moves along a horizontal plane due to constant force F coinciding in direction with the cart's velocity vector. In the process, sand slips through a hole in the bottom with the constant velocity mu kg per second. Oh, find the acceleration and the velocity of the cart at the moment t. If at the initial moment t is equal to 0, the cart. So what do you mean by at the bottom? Sand spills through a hole in the bottom. Okay, so it is going down, right? Yeah. Well, I mean, it's relative velocity. So in the horizontal direction, as seen by this guy, the cart, it's gonna be 0. So it will keep on moving with the same velocity. What are you? Oh, there's a force in there. Sorry, I almost forgot about that. There's this force, and then there's normal vector which takes care of the y direction thing. So we don't have to worry about that. Find the acceleration and velocity of the cart at the moment t. If at initial moment t equal to 0, the cart with loaded sand has the mass m naught and its velocity was equal to 0. Right. The friction is to be neglected. Perfect. Velocity was 0, right? Okay, so what do you know? The acceleration, not as a vector, I just write A, and that's equal to the force upon the mass. So force upon what is the mass? We don't know what that thing is, right? Because it's variable with time. But we actually, yeah, I mean, we kind of do know this. So it's going to be m naught initially was minus the rate at which it is going down, which is mu, and that times the time required. So yes, this is our acceleration at any time t. What we want is it's wait, what? Find the acceleration. Okay, that we just know, right? And the velocity, just integrate this thing. So like v is equal to, it's gonna be negative 1 upon mu, and then you got f over there as well. You got natural log of m naught minus mu t upon m naught, right? Yes. And then plus some initial stuff. So initially the velocity is 0, and that's why nothing. Yes, that should do it. So I'm gonna leave it like that, not change it, because it looks good like this. So there's it. Yeah, acceleration and velocity. Now we know this. Perfect. Okay, 183. A flat car of mass m naught. What's a flat? I think it's flat car, right? Wait, does this mean something? I don't know what a flat car is. Of mass m naught start. I mean, what do you expect me to know? Like, I've never heard this word, okay? A flat car of mass m naught starts moving to the right due to a constant horizontal. Oh, so you have a figure as well. Oh, so it literally is just a flat car. Wow, that's unexpected. Okay, I thought it would be some kind of, I don't know, a name for a particular kind of instrument or something. But it's just like, yeah, plank on wheels. That's it. That's what it is. Okay, flat car of mass m naught starts moving to the right due to a constant horizontal force F. Sand spills on the flat car from a stationary hopper. The velocity of the loading is constant and equal to mu kg per second. Find the time dependence of the velocity and the acceleration of the flat car in the process of loading. Hey, it's the same thing as this guy, but now instead of having minus mu, you have plus mu. Velocity and acceleration once again, right? Friction is negligible small. Okay. And it starts moving, so initially velocity is 0. Yeah, right. Friction is negligible. Okay, perfect. Yeah, it's the same question as this one, you know. There we go. Of course, acceleration is just going to be like f upon m naught plus mu t now, and the velocity will be, so it's not negative anymore, f upon mu natural log of, so I'm just replacing minus mu by plus u everywhere, m naught plus mu t and that upon m naught. Yes, yes, right. So initially it was m naught, yeah, mass m naught, so initially it's m naught and then it starts falling down, of course. Right, next, 184. A chain AB of length L is located in a smooth horizontal tube so that its fraction of length h hangs freely and it touches the surface at the moment when with its end B. Okay, at a certain moment, the end A of the chain is set free. With what velocity will this end of the chain slip out of the tube? Okay. Oh, so first it's held and then you just release it. So now, okay. So in this part, there is tension that's pulling this stuff, of course. And then over here, you also have, I think, tension because, yes, uh, yeah, right, it must be there, right? Then there's this normal force, of course, which makes this sag. So it's zero tension over here, most likely. Yeah, so is it okay to assume like this thing is just free falling? But then A of the chain is set free. What velocity will this end of the chain slip out of the tube? Hmm. Surface of table. So is the table smooth as well? End of the chain slip out of the tube. Which end? Okay. And A, right. So with what velocity will this thing, okay, slip out of the tube? Right, right, right. That's what we want. Um, I don't know. Energy conservation might work. Yeah, I mean, we can definitely do energy conservation, right? Uh, there's this normal force, but then is the normal force actually doing it any work? I guess it might be because I mean the thing that yeah, it will go back a little, right? And after that, it will start to go away, and that's why the normal force is in fact I think doing some work. Huh? Then you got. I mean, okay, friction is not doing any work over here. Tension, it's just internal force. It cannot do anything. It's kind of complicated, isn't it? There's definitely some tension that's pulling this whole thing. Okay, but does how what happens to the tension as we go down? Okay, I think it's okay to assume that the tension is zero right here, wherever it is touching this, right? Is it? Is it okay to assume that? It must be. What else could be happening? Okay, that's zero over here, but then it is positive. So it's yeah, there is tension over here, but then it's not here. So what is happening over here? Okay, this whole thing is like going down. Uh, wow, this is unexpected. One thing we know is that all of this thing is just going with the same velocity along this path. Sorry, the same speed along this path. Yes. Okay. You just have to assume that there is some tension over here, and then there is zero tension over here, or something like that. Yeah. What else? What else can you even do? Okay. But then the free fall condition doesn't make sense anymore. Oof. And what happens to the thing that is now on the table? What happens to that? Okay, please don't do this. What happens to that part of the chain? So, the general condition for this thing would be you got this chain like that. A bit of it is above it, a bit is in the air, and then a bit of it is on this table. So, what happens to this thing? Does it move with some velocity? Does it get stopped due to friction or something? What will happen? Uh, once again, different. Yeah, once again, the problem is with what assumptions can we make? I think it's reasonable to make the assumption that tension is zero right here. I think. What could go wrong, right? What could go wrong? And then let's also make the assumption that this chain is now stationary all of a sudden, right? It's not moving anymore. Is it given somewhere that it's moving? Surface of the table. It didn't say if it's having friction or not. Maybe it's not that important. Maybe even without or with friction, it will give us the same result. So, huh. I mean, I think that makes sense because, um, yeah, I mean, no. Thing is, tension does matter, right? Hey, wait, if there is friction, we know that this complete guy, it will have like a force acting opposite to it, so it will also cause a sag, right? This chain will start becoming like that or something, right? And without friction, uh yeah, without friction as well, I mean, there's nothing that's pulling this, so we can actually assume that there's not going to be any tension at this point, and there is going to be tension at this point. Okay, right. uh No tension here, and there is tension here. How does this make sense? Okay, let's just write down the acceleration. I mean, all of these parts are moving the same acceleration throughout this length, right? They must be, or else it would sag. Well, it is already sagging. Just assume it's steady state, right? If it's steady state falling, then the sag is, I mean, a constant. It's not increasing or decreasing. That means, yeah, we can do that kind of analysis. So for this dx length, yes. So if it has, I don't know, linear density mu, then it's got mu dx mass, right? You might have so some tension over here, and then you got t plus dt over here. Yes. So g minus dt upon dm, which is, so dm is just going to be mu times dx. This thing is the acceleration, right? So you can say, okay, dt upon mu dx, yes, is equal to g minus a. Now this thing is kind of constant, constant with respect to x. I should really use partial derivatives, but hey, whatever. You get the idea, right? It's only varying with space, not with time right now. Acceleration is dependent on, I mean, like, yeah, it's a second time derivative. You get the idea. Thing is, it's just partial t upon partial x, right? Okay, so now that we know this, we can just integrate this. So this will be t upon mu, so delta t, which is like t. So over here you got some tension t, over here you have 0, is equal to, and x, what is x? X is, okay, distance from here. We'll say that thing is x. So this will just be mu times of g minus a times x. Yes. And yeah, let's just say this is not tension t. At this point you have tension t, right? Does that make sense? So there we go. Yeah. Oh, why is this mu over here? So tension is equal to mu times g minus a times x. Okay, that's understandable. Right. And now what do we do? Oh yeah, so once you know what this tension is, you can use this so at this point. So this is h, right? So over here your tension will just be mu times g minus a, and that times of h. But then this is, how much of mass is this though? You got this h length. I don't know what to call this thing. Let's, so I mean, you got this formula, right? We only are going to use this formula to figure out what this thing is, right? So we might not even need this. So get rid of this elemental analysis. And now let's say this thing is, I know I'm using x for two different things right now, but hey, sorry. Yeah, I mean, I can do that. I can do whatever I want. So if this thing is x, right, then this is h, and then the complete length was, I don't know, l or something. So this will be l minus h minus x. Yes. Okay. So this has mass mu times l minus h minus x. Yes. And this guy's acceleration is just a as well. So that will be equal to mu times g minus a times h, because that's the only force on this thing. No friction. Remember, no friction. So there we go. This cancels, right? Then you just get this equation. So, right, I mean, that actually does tell us the acceleration is a function of x, and that's what we want, right? So then you'll just be able to integrate and get this thing done, because we just want the velocity, right? I'm thinking maybe this is not. It's ugly actually. Whatever, it's gonna be a, and then you got l minus h minus x plus h, which is l minus x. That's equal to g times h. So our acceleration, which is basically just v dv upon dx. So yeah, I mean, all of the thing is going with the same speed v, right? So it's doable. So I can also do this for this last point. Makes sense. And that's equal to what was I doing? Yeah, it's equal to gh upon l minus x, right? L minus x is just this part. Yeah. Hey, whatever, just do this thing. So wow, acceleration. Oh yeah, just video. So like v squared upon 2 initially is going to be 0 or whatever. So it's equal to gh, and then you got negative, so negative, and then you got natural log of bad. So negative gh natural log of, so initially x was 0, now it has some x, but we know what x is going to have, right? Like this thing comes like that, all of this length L minus h of length is now over here, so that's our x. It's going to be L minus h upon L. Yes, yes. So now we got the velocity. Nice. Yeah, it comes with the assumption that tension is 0 over here, right? In that way you can do this, and it's no, distributed uniformly. That's not exactly assumption, because the acceleration is the same everywhere. You can do it, right? So yeah, the thing is, like, this path is not actually just a straight line, but something like this, whatever this bendy curve is, right? But the thing is, you can do this for, yeah, for it throughout of this. So in this case, you might just say, okay, x is not, sorry, h minus x is not this length, but instead it's this length, right? And we are just talking about this whole thing happening, so acceleration and everything, about this path only. Does this make sense? Okay, next. Oh, yeah, we have to present the answer correctly. So 185. Oh, yeah, this is 184 that we're doing right away. Okay, so v squared is equal to, what am I doing? I don't want the square, I want the square root and stuff. V is equal to square root of 2gh and then natural log of L upon L minus h. That should do it. Okay, 184 done. Let's go to 185 now. 185 is the angular momentum of a particle relative to a certain point O varies with time as m equal to a plus bt squared, where a and b are constant vectors with a perpendicular to b. Okay. Find the force moment n related to the point O acting on the particle when the angle between the vectors n and m equals 45 degrees. Okay. Find the force moment n relative to the point O. Yeah, whatever. Okay, acting on the particle, the angle between m and n. Oh, this is not that hard. I mean, just take a time derivative of this thing, you will get your n. And then you want the angle between m and n to be 45 degrees. So do the dot product thing and everything. Then once you get that, you can figure out what n is. Yes. So let's do it. What we want is, so uh, yeah, we'll just say a b t squared. So these are just magnitudes now, not vectors. Okay. And yeah, its coordinates are along whatever a is, wherever a is, right? Like that. So these are constant vectors, and that's why I'm using that. So wherever a is pointing to, right, that direction is the x axis, and wherever b is pointing to that direction is the y axis. Okay. And then this dotted with the other guy was, what was the other guy? Right, and it's going to be 0 comma 2 bt. So yes, and then you have to divide by these guys magnitude. So I mean, okay, this guy's magnitude division with that, it's gonna give us 1 in the end, and this will give us square root of a squared plus b squared t power 4, and this has to be equal to our cosine of the angle between them, which is cosine 45 degrees, only 1 upon square root 2. So you can just square this. I mean, okay, that's 0, this cancels and stuff. It's gonna be bt squared right there. This is equal to 1 upon square root 2. Okay, so you can find what t is in this way. Yes, right. So this will give us 2b squared t power 4 is equal to a squared plus b squared t power 4, and that means b squared t power 4. What am I writing? It's supposed to be b squared t power 4 is equal to a squared. Yes. Yeah, and we just want the force moment n, which is 0 comma 2 bt. So what's the time? The time is and it's going to be positive and stuff, so it has to just be square root of a upon b. Yes, so then it's very easy because yeah. And by the way, a and b were positive quantities because I took them to be the magnitudes. Okay, yes. Now that means our n thing will just be 0 comma 2b times square root of a upon b, which is 0 comma, or we'll just write that using vectors and stuff. So uh 2 b vector t times square root of a upon b. Yeah, this should do it. Should really do it. Or you can write it like, okay, 2 square root of a b times t, and then in the b hat direction, right? That does it. This is our n. Let's go to 186 now. A small, what? Sorry, uh, a ball of mass m is thrown at an angle alpha to the horizontal with the initial velocity v naught. Okay, find the time dependence of the magnitude of the ball's angular momentum. Okay, related to the point from which the ball is thrown. Fine, fine, fine. Find the angular momentum m at the highest point of the trajectory if m is equal to 130, alpha is equal to, right? So that time dependence. Oh no. Ah, this position is gonna change. Uh-oh. Really? Uh-oh. Right. It's just going to be complicated. So our r vector is going to be, so it's vx times t, and then you got vy t minus g upon 2t squared, and your v vector is just going to be vx comma vy minus gt. So what you want is mr vector cross v vector. Why? Fine. So that's going to be m, and then you got this cross that it's going to be all of the times k hat anyway, right? So k hat, and then you got, so yeah, positive of this cross that. Yes, yes. So it's gonna be like vx vy t minus vx gt squared, and then negative of this cross that. So negative of vx vy t. Oh, that's nice. At least that cancels out. Oh yeah, actually that is to be expected. Fine. And then you got so negative is positive, positive of vx g upon 2t squared. Oh yeah, nice. So this will just be mk vector, and then you got this, and that's gonna be what? Negative vx g upon 2 times t squared. Yes, that should do it. This is our angular momentum. So our angular momentum vector, which I'll call it L vector, is just negative mvx g upon 2t squared k hat. Right, that's our time dependence. Oh, and by the way, it's thrown with speed what? V naught and angle alpha from the horizontal. So the Vx is just V naught cosine alpha, right? So there we go. Well, L vector is negative. What was this? Negative m Vx. So negative m V naught. Let's use that g upon 2 there as well. So gt squared upon 2. Let me just not do that. Yeah, let's not do that. And you got this cosine alpha, and all of this upon 2, and that times of t squared, and that's times k hat. Yes, that's our angular momentum. Right. And then what do you want? You also want uh, find the angular momentum m. Okay, they are using m vector for that. Whatever. So m vector peak is equal to, right, at the highest point of the trajectory. Does this make sense? It must, right? Yeah, yeah, it does. It does make sense. Okay. Oh, you just want the magnitude, right? Oh, then we don't need to do this k hat and all that stuff. Okay, just gonna be this thing. Oh yeah. And now you want m peak. So the peak will happen when you have the time of flight upon 2 as our t, which is going to be what? The time of flight is just 2u sine alpha. So yeah, 2 v naught sine alpha upon g. So that half of that is going to be v naught sine alpha upon g. Yeah, so it's going to be like what? M v naught squared is going to be g squared in the end. So it's going to be upon 2g. And then you've got cosine alpha and then you got sine squared alpha. So sine squared alpha, cosine alpha, whatever this value is. Oh, they even give us the value. Oh, yeah, that is doable. So you got these two things, just calculate these, right? So first you want this thing to be calculated. Oof, I'm gonna copy this to the next page. Let's go for the first guy. So mv naught g cosine alpha upon 2t squared. What's our m? M is, wait, you didn't give us anything. Oh, you did, sorry. 130 gram. Wait, what's happening to it? Why is my mouse not working? Uh, hey, why is this not working though? Okay, I will have to use this thing then. Ah, I don't like using this touch sensor, whatever. Why is my mouse not working? Nope, nothing, no reaction. Hmm. This is not. Wait a second. Oh, it's still not working. Fine, whatever. Just yeah, using this thing with hand. Anyway, what were we doing? Yeah, we wanna do 186. So mass is given 130 grams. It's gonna be like 13 times 10 power negative 2. Our our what? Wait, why is this 130 G? Oh, G is for gravitational acceleration, or is this like gram? Wait, what do I make of it? Is it gram or not? It must be the gram. I mean, of course, the units wouldn't make sense if it's going to be G as the gravitational acceleration. That won't make sense. So there we go. 13 into 10 power negative 2. Okay, that times V naught. So V naught is 25. That times G, which yeah, let's assume it be 10. That times cosine alpha. So alpha is 45, it's only 1 upon square root 2. Oh god, what? Then you got t squared. So just t squared, yes. That upon 2, right? All of this upon 2. Yes. What is this? I should just leave it like that, right? Because who would really want to calculate this kind of stuff? You got square roots and whatnot. Right? Just do it. 10 power negative 1 and you got 30 times 25, which is like what? 75 and got 25, which is going to be 325. So 3 to yeah, 325, and then you got this point over. It's like 32.5 upon 2 square root 2t squared. This should do it. Minimize. Right, so first answer is just this thing. And the other thing was, when does this actually, yeah, okay, whatever. So you don't need to find what t upon 2 is. No, I won't do that. Just plug it into this thing and get the thing done, right? Yeah. mv naught squared is going to be 13 into 10 power negative 2. We got v naught squared, which is like, okay, 125, whatever. Sorry, 625. Remember doing 625 squared. Or just 5 power 4, right? Then you got less thing upon 2g, so 20. And then that times sine squared alpha. So sine squared alpha is 1 upon 2, and then this times 1 upon square root 2. Yes, that's the thing. That's the thing. In meters, of course. Sorry, whatever SI units are, we are not doing high, we're doing the angular momentum at peak. Yes, so this will be, let's look at it. We got, it's like 10.83, 5 power 4. It's like 13 upon, so 5 power 3 cancels, you got 5, and then you got 2 power 3, and then you got once again 2, and then you times 2 times square root 2 right here. Yes, that should do it. So it's going to be 350 is like 65 upon 2 power, what's this? 5, which is 32, so 32 square 2. Yes, 65 upon 32 square root 2. Okay, so 186 is done. Let's go to 187 now. This is really unfortunate that my mouse is not working anymore. Oh, I wish. Oh no, it's still on, even though I plugged out the. Oh, okay, this is very weird. What happened to this thing? Right, just I'll deal with that later. First of all, 187. A disk A of mass m sliding over a smooth horizontal surface, velocity v experiences a perfectly elastic 1.48. Okay, now how do I scroll down with this? Oh no. Uh-oh. Ah, this is not doable. I can't be doing this with, just hand. Oh, I need this mouse. Fine. So I think I'll see you guys in the next video because unfortunately I can't go on anymore with this. So yeah, bye.